So I'm Sagy Cohen. I'm a professor at the Geography Department. I'm also serve as the Deputy Director of CIROH, the Consortium for Research to Operation in Hydrology. When I am invited to give these kind of talks, what I like to do is give an overview of the kind of research that we've been conducting recently and sometimes not so recently in my lab. So instead of kind of focusing on one specific paper or topic, I like to just give an overview, for better or worse. But because we have a lot of students today, I also decided to make it more, let's call it instructional or educational. So I'll put some more basic concepts as well. I'm not assuming that you all know everything that there is to know about hydrology and geomorphology, which is what I'm going to talk about. So I'm going to talk about two themes that we have in my lab. One is focusing on floods and hydrological extremes, well, in this case, mostly floods. And then my other hat, our other research focus, which is global sediment modeling, which is work that we've been doing for many years. Now, as you can see from these pictures, sort of it's kind of washed out on these projectors, but this is not just me, obviously. So there's a lot of students and colleagues. Some of them are featured here in these pictures, some of them are not. So I'm presenting on their behalf. I'm going to use a lot of we, and that's really we because there's a lot of people who worked. In some cases, I'm going to kind of highlight specific people, but if I forget, and some of them are in the room, so my apologies. I won't forget you, Tree, so you're good. So let's get started. Now, again, usually when I'm invited to give this talk, I talk about CIROH. So I give like maybe 2-3 minutes about CIROH, but I'm pretty much assume that everyone here have already heard quite a bit about CIROH, so I'm not going to waste any time on that. In the odd chance that you haven't heard about CIROH, so CIROH is a new cooperative institute, well, relatively new, just over a year-old cooperative institute between NOAA, the National Water Center, which is within the Office of Water Predictions, and the University of Alabama with a large consortium of other universities and private companies. And its goal is to advance research and community building for the National Water Service, Weather Service. So we have, again, I'm sure you heard a lot about that, and so I'm not gonna spend a lot of time. So I'm going to jump right into the first topic, the first theme of research that we do in my lab, and that's at the currently, since CIROH especially started, and we started working on CIROH-related project, that became pretty much the main or almost the exclusive topic that we currently work on, and that's flood inundation mapping and analysis. So again, I'm going to give you some highlights of what we're doing, but I'm going to start with some basics. So flood inundation mapping, I think the name explains what it is in general, but it is a very important component in the framework of forecasting floods, right? It tells you, it translates hydrological forecasting or observations into the actual geographical location or extents of flooding. And you don't need to be an hydrologist to understand why this is important, right? This is where the rubber hit the road, and sometimes literally, and this is the places that you need to warn people, evacuate people, plan not to have people, and all the things that you need to take care of when it comes to flooding, either operationally or even from a research perspective. Now, in terms of how to generate what we call FIM, flood inundation maps, or flood inundation mapping, there are multiple ways to do that. You can use what's called hydraulic models. These are, you can think of them if you haven't heard of that, it's kind of the fluid dynamics. You kind of simulate where the water is going to go. You give it some input of how much water is coming in from upstream or upland, and then you simulate where the water is going to go using different equations of fluid dynamics, basically. And you account for different attributes like terrain, like topography, like land cover, and so on to do that. These are generally very good solvers, or can be very good solvers, meaning they can produce very detailed and accurate predictions of flood inundation mapping. However, they are fairly expensive in terms of computational cost and also data. You need relatively a lot of data, and you need to calibrate them. So there's a lot of work involved in generating high quality film from hydraulic models. Terrain-based approaches are, well, much simpler. They just use the terrain to try to estimate where the water would go based on the topography, and we're going to talk more about that. And finally, we have observation like remote sensing, so satellites, aerial photography, or even in situ observations, so actual observations of floods. They can be quite accurate. They have their own problems, but they can be a really accurate representation of where floods occurred in the past or in near real time. So remote sensing is great. We're going to talk about that a little bit more. But obviously, they have a limitation where they give you where things were or are at the moment, right? They can't tell you the future by themselves. So let's jump into the way the Office of Water Prediction, which is that National Water Center that you've, I'm sure, all heard about. So the NOAA flood forecasting framework. I don't want to dive too much into the history of this, but a few years ago, NOAA, after they established the National Water Center, they got directive from Congress, basically, that they need to develop the next generation hydrological forecasting systems for the country. And part of that, or one of their main effort, was to develop flood modeling or flood predictions. In a nutshell, what it is, you have the National Water Model, which is a hydrological model that predicts mostly discharge, the amount of water in rivers, in over 2 million reaches across the country. And they had to come up with a way to translate that hydrological prediction into flood inundation mapping. Because this is a big country, and because they wanted to do it at very high resolution, the solution that they opted for is a terrain-based solution, which is, as we said, much simpler, and as a result can be scaled up at the continental scale, basically, or half continental scale, which is the US. And they use an approach called height above nearest drainage. I'm sure many of you are very aware of this approach and the way that they do that. But in a nutshell, you can kind of see these animations that I took from their GitHub, which is you take a digital elevation model, a terrain map, you normalize it based on the elevation of your nearest drainage. That's why it's called, by the way, HAND is one of these very rare occasions when you have an acronym that actually tells you something useful. It's actually what this is, right? The height above nearest drainage. So it's quite refreshing. But anyway, once you know what is the relative elevation of each pixel base relative to its nearest drainage, then if you know how high the water is in that reach for a given point in time, then you can estimate how the extent and depth of the water around that reach. That's the whole concept. There's no hydraulic simulations here. There are no complex fluid dynamics involved here, and that's part of its limitation of that approach. It's purely what we call a bathtub or a terrain-based approach. Now, they use the Manning's equation, which I'm going to talk about in the next slide, to estimate, to translate basically the hydrological predictions, the discharge, into the height of the water, what we call stage or level or water level. And you can see that in the lower animation here. They try to illustrate that quite nicely here with a concept called synthetic gradient curve. I don't want to go into that, but basically this is a gradient curve that translates discharge predicted by the model into water height that can then be spread out across the region. So the Manning's equation, as I said, I decided to do this a bit more. Actually, that's in a couple of slides. Anyway, before I go to the Manning's equation, we have a project that's been now in force for about a year, I guess in full force, where we try to address some of the main limitation or try to improve the way that the height above nearest drainage approach can be applied at an operational framework. And we kind of proposed these kind of tasks, and we started to working on them. We want to develop an observational data set of flood inundation maps. So these can be used to better develop and evaluate FIM operationally. We decided to try to figure out how to better represent what's called the channel roughness parameter. I'm going to talk more about that. We wanted to figure out how to better represent the channel shape, the channel morphology, and then how to estimate bankful discharge. When do floods actually begin? Again, I'm going to talk about each one of these points in a minute. And finally, we wanted to compare different solvers of flood inundation mapping from very complex or fairly complex hydraulic models to the hand, basically, which is our simplest approach, and see if we can come up with a way to optimize film production, meaning in some places maybe we want to use a more complex solvers, and in other places we can get away with a more simple solution. So going towards a more nuanced approach, so not just one model wins them all and one approach takes them all. So I mentioned I'm going to give some introduction here. So I took these couple of slides, a few slides from my river hydrology course, just to give you a sense of what we're trying to achieve here. So in hydrology or hydraulic, we have what's called the continuity equation. That's a very simple concept, very easy to understand. It says that the discharge, the amount of water or the flux of water in a channel, in an open channel, is equal to the velocity, how fast the water is going, and what is the cross-sectional area, right? What is the area of that volume of water? I think conceptually, if you try to think about it, you can understand you have a certain cross-section of water and it's moving at a certain speed, and therefore that gives you the volume of water per time, what's called discharge. So that's the continuity equation. Now, velocity is very difficult to measure, it's especially continuously and accurately across the channel. So Manning's equation was developed quite many years ago, 1795, and it allows us to estimate or calculate velocity in an open, uniform flow in an open channel as a function of some roughness unit here. We're going to talk about that. That's the Manning's N, the Manning's roughness coefficient, the hydraulic radius, which you kind of see represented here, and the slope of the channel that gives you some of the power. And so with all of these, you can calculate the velocity of the water in the channel, knowing all these parameters. Now, it's very simple, but it has been used extensively, still used. That's one of the most basic equations in hydrology that everyone still uses, including, as I kind of quickly showed you, to calculate the synthetic rating curves that we talked about for the National Water Model Center. Now, if you combine the continuity in Manning's equation, then you can calculate discharge because you know what velocity is for Manning's. You have the cross-sectional area that you can estimate, and therefore you can calculate discharge, and with that you can calculate the other parameters as well, including water height. And so one of the sticking points of that approach is that you need to know something about the roughness coefficient. That's basically the resistance of the flow to water. Think about roughness. If you have a channel, for example, with big logs and boulders inside, right? So roughness is really high. The water is going to have harder time to pass or flow very rapidly, as opposed to, let's say, a cement cover channel that allow water to flow very quickly. That's generally the Manning's N. And then we also need to know potentially something, well, we did need to estimate the channel dimension. So Manning's N, the roughness coefficient, is still estimated, either used as a constant in most applications, or is derived from these kind of tables, lookout tables, or you can have some very simple power law equation with bed material size. So there's a bunch of simple equations to do that. Basically, I think it's not very controversial to say that we don't know how to estimate Manning's N in space continuously everywhere in a high degree of confidence. I don't think that's at all a controversial thing to say. And as a result, that's a big sticking point because Manning's N has actually been shown to be one of the most important sources or the biggest sources of uncertainty in, for example, the synthetic rating curve estimation. So we, as I mentioned, we claim or we think that we can do something about it. Basically, that we can do better than just using a constant N, that we can use new data sets that have been emerging. We live in the era of large data, right? So we should take advantage of that. And there are a lot of smart and capable people who publish data that we can now use and use new techniques like machine learning to try to harness that data. And that's what we did. This is the initial effort that we have made. This actually came from the Summer Institute in 2022. There was a project that I was co-leading with a colleague of mine and 3 students that worked on that for the summer. And since then, this paper is actually under review right now. And what they did, they took this very large data set of cross-sectional observation that the USGS took. They take these surveys. USGS take these regular surveys in all their gauge stations. And someone took the time and published that in a very nice data set. And we took this data set, did some data analytics or engineering, and then we used machine learning to estimate that Manning's N again. The premise of this paper is that we found a lot of variability in each location as a function of discharge. And that's quite interesting because it's not super surprising, because when the water gets deeper, the roughness actually gets smaller, relatively speaking, because you have more water, and therefore what's going on at the bed or the banks is actually less influential. However, it hasn't been really considered in the past. So people, as I said, they use a constant N, not only in time, but also in space. So we are, I think the premise or the new things in this paper is that we show that we shouldn't, basically, or that we should try to find more creative solutions to incorporate the time-varying Manning's N. Where we are going with this in our own research right now, so moving forward from that paper, is actually to think about how to estimate this in a more applied way so that can be used in the National Water Model or the National Water Center FIM. And this is our next step. This is part of Rehene is probably going to work on it after she finishes her current paper, which talking about that. So as I showed you earlier, again, one of the important attributes that we need to know, not only for flood inundation mapping, but also for hydrological modeling, is the channel dimension, the channel geometry. Now, it may be a surprise to you. I think it was a bit of a surprise to me when I first heard about it, that we actually don't have a really good way to estimate in channel geometry. You would think in our era where we can see everyone's Google search and where they're going and what they're doing, that we would know how wide and deep each location in our river system. That's actually not the case. So the state of the practice has been to use what's called hydraulic geometry equations, which are very basic power law equations between discharge or drainage area and some attributes to figure out what is the width and depth of a channel in a specific location. These are extremely unreliable if you want to do very high resolution, high quality estimation of channels. And so again, what we decided to do is to harness that same data set actually and some additional data sets to see if we can use machine learning and other approaches to better estimate channel width, depth, and shape. So now we hopefully can do that. And this is a paper that this part of Rehene's PhD work, and she is hopefully finishing a manuscript about it soon. And she's going to present about it at AGU. And so she tested many different machine learning algorithms and some other approaches. And we find a fairly high level of predictability using machine learning of channel width and depth. And so I think we're quite happy, and we hope to basically publish this as a data set to the world so people can use that, both the models and the actual data, to do that. And one of our next steps would be after that to show how this improvement actually translates into better flood inundation mapping. That's obviously very important. So something that we've been working fairly closely with the National Water Center folks to do that. Bankful discharge estimation that I mentioned, again, this is one of those things that may or may not be a surprise to you. You would think that you will be able, or we will be able, to estimate when do floods actually begin, right? At what amount of water in a specific location will we have a flood? So that's called bankful discharge. Bankful is when the discharge, the amount of water, reach the bank of the channel. Beyond that, if you have more water, then you'll start, the flood would initiate, right? The water will spill over the channel and go into the floodplain or whatever is around it. And so, again, you would think that we'll be able to, we will have a good idea of how to do that, but we don't. So the state of the practice has and still is pretty much everywhere to use what's called reoccurrence interval, to say 1.5 year reoccurrence interval, so how frequent or how rare a specific discharge in a specific location, that will be our bankful. So 1.5 year or 2 year reoccurrence interval is bankful. So, you know, again, one in every 1.5 year you will get a small flood, right, or just the crust of a flood. And that's what the National Water Center is still using. They nuanced it a little bit more, but in a nutshell, that's what they've been using. Other people around the world are using the same thing. It's very, very common practice, been used for many, many years. It's very bad. Let's say it like that. They would tell you that. And the student who works on it, Monica Stone, she's actually works at the water center at the operational floor. So she actually deals with these things on a daily basis. And they would tell you that's not working. That's basically not a good way to estimate bankful discharge or the initiation of floods. I think you can understand from an operational perspective, it is extremely important to know when a flood will begin. I'm forecasting discharge into the future, the next 5 days. I need to know if that discharge actually truly translates into a flood, because it's not like what we do or most of us do. It's, you know, research and analysis and publish paper. They need to warn people, and if they warn people inaccurately, people are not going to listen to their warning. So accuracy is extremely important. So they are very interested in this. What Monica has been doing is, again, harnessing the data. A lot of it she generated herself, and trying to link what's called activation discharge. So this is the amount of water that river forecasting centers around the country will initiate a warning. So they have local knowledge, and see how that relates to different reoccurrence interval, different other method of estimating bankful, and also different observations of bankful that people have measured. In addition to that, and this is work that Riley did here, we wanted to know where bankful, how to identify bankful actually from a very, very specific application that we were doing. I told you about our use of this new big data set that take the measurements of USGS of the channel dimension and properties, but they don't tell you when is that each observation or how high this observation is relative to bankful. So if we want to know what is the bankful conditions, we had to figure out a way to try to isolate that. So Riley and Ray, they also have been working on different approaches to try to use different statistics or algebraic approaches to try to identify that. And I don't know if you're going to present about it at AGO. I don't, maybe a little bit, but she presented about it before. And there's some interesting application here that we're also going to use, or she's going to use, to estimating the channel shape. So it's one thing to know the width and depth of a channel. You also need, ideally, would have some idea of how it looks. What's the shape of it? That's not trivial, because we don't have a ton of data on channel shapes. But I think that's quite important, and we can probably make a lot of progress on it using our existing data. Finally, I think, or nearly finally, we do have, as I said, we want to generate a large data set to estimate, to be able to predict FIM better. And in order to do that, we need observations. We don't have that. That's one of the sticking points in FIM development, of FIM model development. So the way the National Water Center is doing that, for example, the way they evaluate the progress they made in their development is to compare their hand-based approach to HECRAS, so models. So they take models that were developed by FEMA and others, very high quality models, but they compare their model to another model because that's the only data that they can compare against. So model to model comparison, it's not it's not the end of the world, but it's not ideal, right? Because obviously two models can be wrong because of the same reason. So I always thought that compiling a large observational data set is extremely important, and I think the water centers and people outside of the water center would agree with that. So this is something that we started to do. Dan Tien is here. She's a postdoc on this project, and she's starting to use developing different approaches to use remote sensing to basically develop flood inundation map data repository that we're going to share. However, that sounds great on paper. Remote sensing is not perfect by any stretch of the imagination. And so we have a problem. We want to use remote sensing to evaluate FIM, but the remote sensing data is not perfect, right? It cannot see in almost any instance under dense vegetation, in buildings or in built environment, it struggles a lot. So we have an imperfect data set that we want to use to evaluate another data set. So what do? Either we don't use it or we try to find solutions to do what we call robust and fair evaluation of the model. So this is something that we are currently working on, and Dan is working on a paper on one of the approaches, which is basically, in a nutshell, I won't go into that, but we're trying to guess or to estimate what is the true extent, or more or less the true extent, of the flood using remote sensing and terrain and land cover, and use some hopefully smart statistical approach to say, okay, given this data, we have a lot of uncertainty, we can evaluate our model with this specific statistical approach. Hopefully we'll get some, I think we can get some real progress in the really near future. I'm really excited about it because surprisingly, I was kind of surprised, again, one of the surprises that there hasn't been a lot of work on this at all. And people just use remote sensing to evaluate their flood inundation maps where they shouldn't, or they shouldn't do it the way they did. They just did it because you can, right? And that was not a good thing to do. A lot of people did it without thinking too much about the fact. It's kind of a classic thing in sciences where you are very aware of the limitation of your own subfield, right? If you're a modeler, you're very aware of the limitation of your models, but someone gives you a remote sensing product and you say you don't really know much and you just take it as is, saying, oh, this is probably pretty good, right? I can use it as is where you really shouldn't. I actually heard recently from, and vice versa, by the way, I talked about it with a colleague of mine in a conference recently who's a remote sensor, and he said, wait, why do you want to use remote sensing to evaluate models? We use models to evaluate remote sensing because they're much more accurate. And I said, well, yeah, I don't think so. The modelers would disagree with you on that. But everyone is very aware of the limitation of their own methodology and their own subfield. Anyway, I think we can make a big improvement here. I'm quite excited. Let me skip over this thing because I just don't have time. Very quickly, this is a paper I published with a colleague and a student a couple of years ago, actually been really well accepted in terms of citations. This is a topic I'm very, very interested in. So I mentioned the way the National Water Center is estimating flood inundation mapping. However, that approach, one of its limitations, it cannot really work in urban settings because it's very simple terrain approach. It doesn't take into account the stormwater infrastructure and all the man-made issues and the terrain, the subterranean, and all of that. So urban flooding is a topic of considerable interest and importance. Of course, that's where people are. I always tell to people, flood is not a disaster, right? Flood is a natural phenomenon. Only when people get impacted by it adversely, I should say, then it's a natural disaster. So then the places where most people are impacted by floods, in many cases, are where they live, which is urban areas in most cases, especially in the US. And so we need to do better or figure out how to predict flood in urban areas better. And this is one simple project that we had, as I said, a few years ago, where we took the University of Alabama campus, we mapped and simulated the stormwater infrastructure within the university campus, and we did some experiments, modeling experiments. So what happens if you don't include the stormwater infrastructure? What is the impact on flooding? How important is stormwater infrastructure in urban simulations? It's funny, you talk to some people and they say floodwater infrastructure is not important at all in urban flood inundation mapping. The logic behind that statement is that once you have enough water or enough rain coming, then the stormwater infrastructure is overwhelmed and therefore it's going to flood everywhere. There's some truth to it, especially when you think about blockages. That's often a problem in the urban areas, right? There's just leaves and branches and whatnot that blocks it. But even if you don't include this very complicated thing, what we have found in our analysis that it does make a very significant difference, even for very extreme rainfall events like 1 in a 100-year event. It does make a big difference in the amount of water that will be simulated. Again, this is all simulation, yeah, anyway, this was a really nice study, and I really hope to do more in terms of urban flood, and I think we absolutely have to. There's no choice. All right, so I have a little bit of time, not a lot of time, to talk about the other topic, which is global river modeling. Sometimes I need to convince people why this is important. Why do you even care, or why would you want to simulate or model global scale or rivers at the global scale, or global rivers? I think these days you don't need too much work to convince people that that's important. We all know we have global issues, right? Climate change, population changes, everything is connected. And so there is, I think, a lot of value, or I would argue there's a lot of value of thinking globally, or also thinking globally, not exclusively globally, but thinking globally and framing local knowledge or regional knowledge into global scale estimates. And so over the years, we developed different models to try to simulate, especially sediment. That's what I'm going to talk about today. And one of our main motivations is to think about climate change and anthropogenic changes. So provide frameworks that people can think about, okay, what's going to happen if, or what happened in the past because. So human change and climatic changes. That's what models are really good at, right? Doing these kind of experiments. So we developed a model called WBMsed that was at the time one of the first global scale sediment flux models. Since then, there's been quite a renaissance of global scale modeling of rivers, especially of sediment. And that's actually coming after the realization that sediment movement or sediment flux in rivers is actually really important to the carbon flux analysis or exchange analysis at the global scale. So there's been more and more interest from the climatological community or Earth system science community into rivers and sediment fluxes. Now the model, this specific model, WBMsed, it builds on an existing framework that already existed for quite a few years called WBM or WBM Plus. WBM Plus is a global hydrological model that predicts, well, discharge and soil moisture and all the other hydrological fluxes at a global scale. And what we did, we developed modules within that framework to predict sediment and, as you'll see, nutrients a little bit. And this 2014 paper was actually the first time that I really started thinking about channel geometry. So going back to what I presented earlier, because what I realized at the time is these models, and pretty much any hydrological models, don't have floodplains, meaning they basically have an infinite capacity or they assume an infinite capacity of the rivers. So they think of rivers as these channels that have infinite size or depth, and so they can move as much water as you would give them. Because they didn't know how to do flooding and floodplains and so on. So this was my first attempt to think about it. So I developed this module within this hydrological model I called it the virtual floodplain component, which is basically saying if you are above bank full, then you just store the water there temporarily. It's very simple. And then once the water recedes, you kind of introduce the water back into the channel. So it kind of mitigate the flow of the floods. Of the flow, basically, of the hydrograph, and that was actually quite successful in doing that. But that got me thinking about bankful, going back to what I just presented in a more application way, and channel dimension. So this was my first attempt to think about this concept. This was almost 10 years ago since this was published. So as I said, we introduced sediment into this. At first, we looked at suspended sediment. Suspended sediment is that fine grain sediment, mostly silt and clay, that move through the water column or with the river in suspension. So it's always in suspension within the water column. And once it obviously reaches the ocean or a lake, it then can get deposited. So we use this, what we call semi-empirical equation that others excuse me, have presented to estimate that globally. And in addition, we introduced this particulate nutrient and organic carbon equations that some of our colleagues presented in the past at the global scale. Unfortunately, we never published this, but it is a module that's available within our model. Just to give you a sense about this kind of scale of models. So these models obviously need to be pretty efficient. We run this at the global scale. We run it at what's called 6 arc minutes. So it's about 11 by 11 kilometer grid cells. So it's relatively fine for a global scale analysis, but it also gives you a sense this is a pretty large chunk of Earth, right? 11 kilometers. We run it on a supercomputer. You don't have to. You can parallel that a little bit, and that will help you. We mostly use it on a supercomputer just because it takes a lot of data. It generates a lot of data, and it consumes a lot of data, or there's a lot of input data. And so it's much more efficient to use it on a cluster rather than on your personal computer. But again, you can do that. It takes about 1 hour to simulate 1 year. So you can run it for quite a long time if you have the data. And you get, I don't know if that's kind of washed out, but it does give you a pixelated or a pixel by pixel analysis. But we usually, in my papers at least, I like to convert or to extract the rivers in a vector format so I can better represent it, because otherwise the pixels are too small. It's really hard to see at the global scale. So this is kind of the typical presentation that we see in the papers, but it is a pixel by pixel representation. Now you can also run this at much higher resolution. The highest resolution that I attempted to run this was for the Hawaiian island of Oahu at 30-meter resolution. Oahu is kind of a very interesting case study for both sediment and discharge. These tropical islands are pretty fascinating. And Oahu specifically have a lot of gauge sites from USGS, or relatively, for each size. I don't know if you can see those dots on the map. And the model actually performed quite well. Surprising, very surprising, I must say, for discharge, not so much for sediment. I should say, by the way, those of you who are modelers, these kind of models are not calibrated. They could, but we have not calibrated this model because at the global scale, it doesn't make a ton of sense to calibrate them beyond their original equations, because you improve them here, you make them worse there. So these are not usually calibrated models. One thing that I really enjoyed with this line of study is the fact that other groups, either colleagues or sometimes people that I really don't know, just the other day I got an email requesting data. They want to either use the model themselves or they want just to use the data. And over the years, there's been quite a few papers that came out that use this. This is one that I really like to highlight. It also got quite good reception by the community. This is a work by Frances Dunn, who at the time was a PhD student in the UK. Now she's in the Netherlands. She's still a postdoc to my knowledge. And what Frances did, she said she wanted to look at the future. So in terms of climate, socioeconomics, and dams. Like, what is the future potentially going to be like the end of the 21st century in terms of the amount of sediment that's going to flow into the 47 largest river deltas in the world? That was just the topic of her dissertation, PhD dissertation. She learned how to use the model. She implemented all of these data set. And she did a very detailed analysis of all these 47 deltas. In a nutshell, it's a very complex paper. You can spend 2 hours just on it easily. But what she found was that on average, we're going to, according to the model at least, we're going to experience quite a significant decline in sediment flux to delta, which is really bad news, because deltas, those of you not very familiar, river deltas, are basically an equilibrium between the amount of sediment that goes into the delta from the upstream river and wave action. Excuse me. So how much energy comes from the ocean to move that sediment? How much sediment is coming from upstream? Once you mess up with this balance, the delta is going to change. If you cut off or reduce the amount of sediment, usually delta starts to erode or sink, and that's very bad for the people who live on deltas, which is hundreds of millions of people, and a lot of agricultural productivity in those deltas. So she looked into this for each one of these deltas. She saw a net decline in sediment, mostly driven by dams, by future dams, existing and future dams in large river basins. I'm going to skip that. You know what, let me skip because I'm running out of time. A very recent paper we just published with Nishani Morogoda, who's just finished her PhD less than a year ago, was something that I've been very interested for many, many years, which is to think about sediment trapping behind dams. I kind of mentioned dams before. Dams on rivers, especially large dams, are the most important distribution or disturbance for sediment flux in rivers. Not surprising, right? You put a dam, you create a big reservoir behind it, sediment would settle, it would not move downstream. And that makes a huge impact on the sediment dynamics of a river system that has implication, as we said, on what's coming out at the coast, so deltas, and also the aquatic life within and water use and so on and so on. The problem is, we know that. It's been demonstrated time and time again for many, many years. However, we didn't have a good way to estimate how much sediment is trapped behind deltas, because we just don't have this, behind dams, sorry, because we just don't have the data. And that, as a result, that became one of the biggest sources of bias in models that predict sediment flux in rivers. So we very excitedly used a data set that was developed by my colleague, John Gardner, where what John did, he used Google Earth Engine, so satellite imagery, to map or calculate sediment concentration in rivers wider than 100 meters all over the country, the entire US. Other people have now doing similar things globally, including him. So this is a map, or a profile, longitudinal profile of the amount of sediment in the river. This is the Missouri River from most upstream over here all the way to the confluence with the Mississippi. And the Missouri River has a lot of large dams on it. And what you can see very clearly, right, once you hit the reservoir, so the reservoir can be many, many kilometers long. So here's the dam at the point, here's the reservoir. Once you hit the reservoir, sediment concentration drop dramatically. Again, very expected, nothing too exciting here. And then, actually, in most cases, we do see a recovery happening after that. But what we tried to do in this paper was to actually develop a model to predict that we can then put in our global model to actually simulate that better and have a better understanding of sediment trapping. And that's what we did. I think there's still more work that should be done to improve that. We're always limited by data, especially globally. But I think in the future we can do a better, even better job. This model works fairly well, but we can do better. I think I'm going to stop here just because we're out of time. Those of you who are, I don't know if anyone here is particularly interested in sediment, but the latest paper that we published in WRR on this, we actually introduced bedload sediment into the global model. This was a paper that I was very, very happy I was able to finally publish, because I started working on it when I was still a postdoc, and it's been kind of back burner thing for years and years and years. And this is probably one of the one paper that I was most excited about, maybe since I was a PhD student. You know, as a PhD student, you're very excited when you get a paper. After that, I hate to say it, but after that, the excitement kind of goes down. But this one, I was very happy to get published. Anyway, I'm going to skip this data, and I'm going to finish here. And happy to take any question. We have just a few minutes for that. Thank you.